All right, we're backtracking a little with homework 1, part C, Cartesian parameterization, deriving the expression for an end cap. So drawing that end cap, we'll have a circle with a liquid level H. We also have the middle point, and from there we can draw our radius. This can be labeled as Z, and then there's actually going to be 2 of these. So our first step is to find this distance here. So that is using Pythagorean's theorem. Very simple, is going to be r squared minus z squared. But again, there's going to be 2 of these. So force is going to be equal to pressure times area. From there, we're actually going to integrate with respect to our area. And our area we know is going to be this here with respect to a changing depth. So we're going to take this whole thing and the dz and plug it in here. And then we can define our pressure simply as rho g, and then instead of our h, we want to figure out here, which is going to be h minus our r plus our z. So that is going to give us our pressure height that we will need to account for. So then this will be plugged into here. And then going forward with these substitutions, we can find that F is equal to the integration of rho g h minus r plus z times our 2 r squared minus z squared dz. And this is going to be from 0 to h, depending on how high this is. So I guess pulling out our constants, we won't be able to actually integrate today. Rho g, well, we'll put our 2 first. 2 rho g, and then integrating, that cancels this and this. I prefer to do that in red. And leaves us with our variables here. And that will be our final answer for this part. I was halfway through recording this and it cut me off because I didn't have iCloud storage apparently. So we had to declutter my phone. So now we are working on homework 1, part C, question 2, deriving an expression for an end cap similar to the other one using polar parameterization instead of Cartesian. So I'm going to draw a nice little diagram here. So getting started, we can label this as R, and then these are going to be our H's from, well, the height to the bottom, or bottom to the water level height. So this is our radius here. We are able to find this distance by knowing this is also R and subtracting radius from height. So that's going to be that there. And then we can redraw this diagram as we are going to take little section bites around for our area. in this instance instead of the last one. So this one is going to be our theta naught, because that was our initial one that I drew, and that is going to end up equaling inverse sine of h minus r over r, because of trig principles, opposite over adjacent, or opposite over hypotenuse. And then this one is just going to be theta. We can do similarly to last one. Pressure times area is going to equal our force, and then a step further there. So our differential area for this one is going to equal, it is, okay, r cosine theta with respect to z, with a dz, and we are going to need to change this to incorporate a d theta, because we can't integrate like that. So first we can determine what z is, and that's actually going to be 2r sine theta. And if we derive from here our dz, that's going to be 2r cosine theta d theta. So we'll end up substituting that into there to get our differential area. I'll erase these little scribbles here. So the next part that we need, we've got that taken care of. We're going to need our pressure. Now our pressure is equal to, this one is equal to our cosine, no, I'm sorry. It's our, like the last one, rho g, but instead of what we did prior, we multiply by our radius, and then we have to make sure we don't double account for this guy here. So we'll actually end up doing sine theta naught minus that sine theta to make sure that we are not, to make sure it's the correct pressure. So using this, oh goodness, using this and this and this, we are going to be able to get everything we need here. And then that's going to look like F being equal to the interval of, we can start with pressure, rho gr, and then our difference in sine thetas between the two. And then multiplied by our area, our differential area. And then that's where we plug in our dz, cosine theta, d theta. So from here, we are going to get rid of, or bring out front, I suppose, this guy, and 3 r's, and a 2. So 2 rho g r cubed, integrate from, I'm going to put our cosines first, and then that gets rid of these guys. We'll make it match in red. Oh, and then our sines from our pressure with d theta at the end. So that should get rid of all that we have there. And where are we integrating from? We're actually going to integrate from negative pi over 2 to what we decided this is, which is this guy up here. So that's going to be from inverse sine of h minus r over r to the bottom is negative pi over 2. So what we have here is the furthest we can go. So that is going to be all for homework 1, part C. Question 2.